Okay. I'm Ray Jenkins, and this is Understanding eBPF in a Hurry. Why it's in a hurry is because we have like 20 minutes. It's a pretty big subject. I work at Segment. I'm a software engineer. I'm not a performance engineer. So I've been digging into this stuff. I'm really excited to be here. Thanks for coming and listening to me talk and present about this. But I've been really excited digging into this stuff. I work on distributed stream processing systems primarily, and really up in user space. So I'm not generally like down in the kernel and stuff. But over my career, I've worked with a lot of people who are kernel developers or network programming engineers, and it's always been something that interests me. So this eBPF stuff is giving me the ability to sort of go spelunking and digging into the kernel. We're starting to use it at Segment. And so I thought it'd be interesting to do a talk on how it works and to get familiar with it from a software engineering perspective. How many people here are using eBPF today in production and actually solving problems with eBPF in production? Okay, cool. Okay, cool. Yeah, so we're just starting right now as well, and it's relatively new, but I think it has really has the ability to be transformative, and I guess we'll talk about that in a bit. But let's start with any performance talk. Should start with you have a performance problem. So and that could be any number of problems, whether you're a developer or a performance engineer. You may have people saying, "Oh, this box is slow; it has slow I/O," or maybe you're losing network connections or just randomly dropping on a service or a set of boxes. Maybe something's crashing and you're not exactly sure why. Maybe something seems slow and something might be getting starved for whether it's CPU or disk or network. Any sort of problem like that, someone at some point, if they haven't already, is probably going to suggest to you, you might be able to solve that problem with eBPF. And now you'll have two problems. So just like any good technical solution essentially requires learning something new. So you've got to solve your problem, and you also have to understand what eBPF is. So the goal for this talk is to see if we can get an overview of the system and understand like sort of how it works and how we could use it. We could do a talk about specific problems you could solve with it, but I thought it would be better to kind of get an understanding of the overall system. So this is our map. I tried giving this talk without a map, and then I realized as I got through the phases that I need a map. This map is generated, this is Brendan Gregg's map, who I think actually might be here. I borrowed it. Hey, Brendan. I thought about making my own, but I figured if it was good enough for Brendan, then I'll just use this one. So this is our map of eBPF, and we're going to refer back to it as we walk around the system. But what is eBPF? So fundamentally, eBPF is a fast and safe, in-kernel, register-based bytecode virtual machine. That's like a huge mouthful, right? But basically, it's a virtual machine that runs in the kernel fundamentally. And it's bytecode-based, and the reason why it is because it's designed to be JITted with a direct mapping to your underlying CPU architecture. So x86, 64, or other modern architectures, the actual instructions in the registers can be mapped directly to the underlying system. So it's fast. It's safe because it runs inside this virtual machine, and we'll talk about that in a bit. Programs get verified so that you're sure that they will operate and finish within a specific amount of time. They can't get into endless loops. And there are several other invariants that need to be observed. When you write eBPF programs, you attach them to code paths inside the kernel, and then when those code paths are executed, your code is called. So it's actually been in the kernel for a bit, since 2014 on 3.18, but you want to use at minimum pretty much usually a 4.1 because that is when kprobe support was added. This is just an example of, by default, if you run a make menu config, you'll see it's enabled, or you can look in your boot config and observe that BPF is on and just-in-time compilation is on as well. There's a couple other components to eBPF. So when you write your programs, you generally write them in a restricted version of C. and you use Clang to compile them down to bytecode. GCC doesn't have a backend for BPF yet, but they're actually working on that. There is a EBPF verifier, so that's really the safety mechanism with EBPF. So when you write your program and you compile it, before it gets loaded into the kernel, it passes through a verifier. And as I mentioned, the verifier makes sure that there's no loops, there's no backward jumps in your program, no unreachable instructions, there's limitations. You can't just read arbitrary kernel memory, stuff like that. And then once your program is executed, you can send data back to user space through either eBPF maps or through perf events, through a ring buffer, which is fast, and you have bidirectional access to that data. So you can actually send through eBPF maps, you can actually send data to your eBPF program as well. And then there's a set of helper functions that allow you to basically, based on the context that your program's running, there's a set of helper functions that allow you to access different functions in the kernel and do intelligent things with the stuff that you're getting. So the amount of features are constantly growing. There's a link here, but it's huge. So this technology is being applied to sort of anything and everything in the kernel, and it's constantly growing. Why do we need this? Because you can do this stuff. I mean, you can instrument the kernel just using kernel modules, but basically with eBPF, it gives you the ability to dynamically and programmatically write something, and you run inside the kernel in this safe virtual machine, and you can trace anything in kernel space or user space safely and efficiently. So that's an overview of what eBPF is, but really the power of this thing is the data sources that you can attach to. So let's take a moment to talk about the data sources. For different people, it's interesting for different reasons. Like I said, it's being applied to all sorts of things inside the Linux kernel. But for performance engineering, the stuff I've been focusing on, and most people do, are kprobes, trace points, user-defined static trace points, and perf events. Trace points are static places in the kernel where tracing is inserted. And you can actually just basically, if you go take a look, I'm going to run some demos while we're doing this too, but if you go start grepping for trace points in the kernel, you can start to see, you'll be able to find a whole bunch of trace points, or you can do a, let's see, you can do a perf probe list. But these are static trace points in the kernel where these are static points in the kernel where developers have defined events that you want to be able to trace. Sorry. 1 second. Is that it? There we go. So there's an example of all of different trace points. And so, for example, if we want to like grab things like looking at block IO, we can do that as well. And so we can see all these specific places that we can trace. Kprobes are like dynamic probes that allows you to essentially break into any sort of instruction in the kernel. And you can actually go look at the kernel and dump basically all the symbols, and you can actually even break inside of an instruction with a kprobe. But generally, we tend to use these kprobes on individual functions inside the kernel. So if you look at /proc k-allsims, these are basically all the functions inside the kernel, and you can let's see. So let's see. And you can trace basically any one of these. So if I run, for example, sudo trace do syslog, I can start tracing any function. I can start tracing. We have to wait for something to actually do a syslog, or let's do sys open. So I can dynamically hook into any of those functions in the kernel and start tracing, and I can see the process that's doing it and that it's calling sysopen, for example. So there's a little bit of detail there about how K-probes are instrumented. Historically, they were slow because basically the way a K-probe works is it finds the instruction that you want to probe, it makes a copy of the instruction, and it inserts a breakpoint. And then when that breakpoint is hit, the control is passed to the probe, and it actually single steps through the instruction, and then it returns. But recently, K-probes have actually got a lot faster. So it's been optimized, and that's enabled by default in the kernel. It's actually on in x86-64. So it inserts a jump, and it's able to find the fast path out. So it's not as fast as trace points, but it's more powerful because you can instrument anything. And here's an example of running a K-probe and tracing TCP send message, for example. So here we can see the individual processes, and we can see every time TCP send message is called. Here's a couple other examples. Here's an example with K-probes tracing actually sysopen and looking at the actual value that's being passed as an argument, the file that's being opened. So we can see the actual file that's being opened. I'm running Foundation DB here, so it's constantly opening a lot of files. It's a database. Here's an example of a U-probe. So a U-probe is like a K-probe, essentially, but it's in user space. So here we're running a U-probe that's connecting to bash read line. So another source of data is perf events. I've heard it referred to as the nearly ungoogleable. Apparently, it's not like extremely well documented. I did put a link up there to a page that is like one of the almost official pieces of documentation about perf events. This gentleman up here who maintains that page collects a lot of data about perf events. But with perf events, you can trace and count trace points in lower level events and also lower level events, basically like hardware events as well too. It has a bunch of other features. One of the things that's probably the most important about those, it has a very fast ring buffer that allows you to share information from kernel space back into user space. And so this is an example of using perf events to basically trace hardware, essentially hardware trace points. And you can collect data from perf events as well too. And then user-defined static trace points, it's misspelled actually. That's supposed to be basically user-defined static trace points are similar trace points in the kernel, but in user space. So for example, here we're looking at libpthread, and we're looking at, you can run this command tplist to see all the trace points. And then here's an example of tracing, like for example, pthread start. So those are examples of most of the sources that we're currently using today at Segment to instrument and write EBPF programs. So let's take a step back and look at the actual programs themselves. A good way to get started with this stuff is to install BCC tools or BPF CC tools, use the package manager for whatever operating system you're using. But basically, there's a lot of tools already written that sit on top of BPF, and it's a good way to get started to dig into this stuff. So for example, this is an example of a tool called biosnoop. So let's run that. And essentially, we can see when we run biosnoop, we can see broken down per process, per PID, block I/O operations against the device, the size of the operation, and how long each operation is taking. Here's an example of a program called run queue latency, and basically it traces, and here we're breaking it down by PID. So we're tracing how long it takes for a process to get added to a queue, waiting to get on the CPU, and then to the time it actually runs. There's a bunch of multi-purpose tools in here as well too, and these are a bit more complex, but you can pretty much use these to trace any of the things that we talked about, like K-probes or user probes. So this is an example of running trace, and we're tracing the malloc call in user space. And we're actually, we're saying we want to trace the calls and then each call by size, and then it's broken down by process. So these these are some simple programs to get started. And if you dig in there, so what do they look like? So this is not them. This is an example of one way to write eBPF. If you had to write eBPF like that, I would not be writing eBPF like that. Basically, I wouldn't be using it at all. You want to use this stuff. It's called BPF compiler collection. And basically, the folks that are working on eBPF inside the kernel are also writing this stuff. And they're writing bindings in higher level languages that make it a lot easier to use. So this is an example of the sync snoop program. And I think we can why don't we just go ahead and run it. So let's see. So if I run, let's see, sudo sync snoop. Okay. Let's go over here. So every time we call sync, right, it's handling that. So let's take a look and see what that does. So okay. So this is a pretty straightforward example. Right, so we have a basic data structure that has a timestamp, essentially unsigned 64, data underscore T. And then we have a macro that basically defines a channel of a perf event ring buffer of where we're going to send these responses. Then there is this function called syscall underscore underscore sync. The syscall underscore underscore bit, there's a little bit of code generation magic going on with eBPF. So, so what that's doing is basically it says it wants to bind to the sync syscall. And then here, each time that this is called, we generate a new data structure, we grab the time, and then we're submitting that result on the perf buffer. Okay, let's see. All right, this is a bit more advanced program. This is biolatency. I think we're starting to run out of time, so I got to move past that one. So let's talk about the VM a little bit and how that's implemented, though. So I lost the map. We're going to go back to 1992 for a bit. So probably most everyone here knows how BPF works. Maybe you don't. If you don't, let's do a quick review. If you've used TCP dump, you've used BPF. So when you run TCP dump, for example, I'm just saying let's dump IP and UDP here. You get something that looks like that. But if you run it with a -D, you'll actually get a set of instructions. And so that's because TCP dump basically passes your filter into libpcap, and that gets passed into BPF inside the kernel, inside the VM, and then the packets are filtered and passed back up into TCP dump. So BPF, I mean, the main takeaway from this is that eBPF was essentially inspired by BPF's design. BPF is a much more simpler system, though. So it's essentially it runs inside the kernel, same register-based virtual machine with a limited instruction set, except it has 32-bit wide instructions and it only has 2 registers. So we can actually interpret this stuff relatively easily. So if we look at the output of TCP dump, for example, what it's doing essentially is it says load in the first 2 bytes from the packet at offset 12, and that's basically the ether type frame of the packet. And then we're saying if it equals 0x8, then we're looking for an IP packet. Otherwise, for example, if it's an ARP request or something like that, that frame will be different, and we'd end up dropping it. So jump to instruction 2 if it matches, otherwise jump to instruction 5, which is the end. And then we continue and it says load up a byte at offset 23, which would be looking for UDP. And same thing, if it matches, go ahead and hit instruction 4, otherwise go to instruction 5 and return. So that concept is basically, so that's BPF, and that gives us a little bit of understanding how the BPF virtual machine works. The eBPF virtual machine is essentially an extension of that. So it's 64-bit instructions. It has 10 64-bit registers. It has a new BPF function call that actually allows you to call other functions inside the BPF virtual machine faster, as well as kernel function calls by taking advantage of some zero overhead mapping between the BPF registers and the actual kernel function calls. And then there's the addition of BPF maps. We might not have time to get to all those, but we'll talk about that a little bit in a few moments. The BPF programs, as I mentioned, are loaded with a syscall. When you do that, there's a couple different ways. When you make a syscall, you pass in a command, and there's a couple different options there. When you're loading a program, you use the BPF prog load option. You can also use the BPF syscall to create maps as well. Now, it's not as trivial as just making a BPF syscall. I actually did an strace to show you what's going on. So there's actually several steps, and there's a good reference at the end of this document on how to go about actually doing this by hand if you wanted to. But there's several extra steps. There's a couple ioctl calls that you have to make. You have to write certain config for the kprobe to certain file descriptors that are returned after you create the program. So it's not as trivial as just making a syscall, but it is doable. But it's better to use the actual the BCC libraries. It makes it much more simple. So a little bit about I want to talk a little bit about the actual EBPF implementation. I'm about to run out of time. I wanted to dig into the actual difference between the EBPF virtual machine and the BPF machine. You can, when you're writing EBPF code, you can actually put it in debug mode, and this is actually useful because as you're writing EBPF code, the verifier can be a bit complicated. You can hit problems that aren't exactly obvious. So putting it in debug mode allows you to get a dump of the actual instructions, and you can step through those instructions and understand what your program is doing at a lower level. We're not going to have time to cover that. And then so lastly, I guess I just want to talk about the EBPF maps. So one of the most powerful pieces is after you've hooked into an instruction in the kernel, you've observed some sort of behavior, and now you want to collect that information and feed it back into user space. A lot of other tools require that you have to copy all that data back into user space. You can use EBPF maps or perf output to share that with zero copy from your user space applications. So there are several different types of maps, and these are growing all the time. They're called maps, but there's actually there's hashes, there's arrays, and there's histograms as well too. There's LRUs, so there's several different data structures that are available to you. And there's also several different helper functions. The most important of these are you can't read arbitrary memory, so any sort of reads of any data that's being passed to your function has to go through BPF probe read. But there's a link here in this presentation to all the functions that are available to you from inside your program. And then you have a set of map functions as well too that are helpers, so it makes it easy to get data in and out. So a couple minutes and then we'll wrap up. So I want to talk about some use cases of how we're using eBPF at Segment. So our first use case is this program we built called NetSniff. So we're entirely on AWS, and actually, well, that's not true. We're on GCP as well too, but most of our infrastructure is on AWS, and we spend a lot of money on cross AZ costs. So we're using eBPF to basically track TCP sockets between all of our services and TCP connections, and we've basically drastically reduced our cross AZ costs with this. The next project we have a project called Segment.io eBPF it's written in Golang, and it's deployed across our infrastructure that allows us to write eBPF programs and deploy to any auto-scaling group. And we have a series of agents that basically run the programs, and it performs, so we'll run our programs and it does stats collection and stats aggregation, publishing out to third-party systems like Datadog. One of the other problems that we've had to solve as well too is basically Docker. So anytime you're doing anything with eBPF in like a containerized environment, it's hard to differentiate. You can't differentiate between the data that's coming in by PID and the container, unless you basically add some additional instrumentation, because you're seeing everything from the OS perspective. So we've created a service registry for Docker, and then so any metrics we're collecting with our eBPF implementation, we can map it to individual services. So a couple examples of things we're using. We're using BioSnoop. We've ported that so that we can watch several services and look at block IO latency. We're tracking all processes for kills, so sometimes we'll have runaway processes where people are just eating a tremendous amount of memory and getting killed, and folks don't know why. They think that maybe they weren't even sure that they didn't realize why their systems were going down and that they were getting killed. And then we actually also collect eBPF metrics or metrics on the actual processes themselves. So